Hello everyone. Before we start, I like to set some fundamentals, some foundations to calculations, and then we can apply them as we go along solving the questions, okay? Number one thing is we established that pressure is rho D. Now, what I want to point out here is that this D is the depth of water column from the surface to the point of reference. Okay, very important, please. It has to be from the surface down to the point of reference. That's D. The second thing I like to point out is that it depends on the situation. If you're asked to find the pressure going downward, vertically downward, on an horizontal surface, so we can have a horizontal surface and we can have a vertical surface. Example of horizontal surface is keel, okay, flat keel. An example of vertical surface is gates, bulkhead. So it's very important to know. An example of horizontal surface can also be the lid of tank or the crown of tank. So if the question says or is dealing with horizontal surface, then obviously D, we don't manipulate D. The depth is just the depth. Let's say this is the keel. Let's say this is the keel of the ship, okay, or of the box or tank. There's the bottom of the tank or the keel. Another thing I will put here, lest I forget, is tank bottom or tank top. Okay, all right. So here, if this is the flat surface, okay, horizontal surface, then that means the depth is going to be from this surface to, okay, to that reference point, okay, to the keel, to the lid of the tank, to the crown of the tank, the bottom. Okay, we don't manipulate that. But if it's a vertical surface, then we now have to check the shape occupied by the water. Okay, so if it's just a rectangular bulkhead or gate, then it's going to be D is going to be from the water surface, okay, to the centroid, okay, center of gravity. It could, and the center of gravity, if it could, let's consider a triangle, okay, so it's going to be the center of gravity. If it's a square, then again it's going to be the center of gravity. That's where we measure D up to, from the surface, okay, from the surface. All right, so it means if this is the breadth of this and this is the length, this is the base, this is just LL, right? Now we can say that the centroid, we know already that the centroid of a rectangle, we can also say the center of gravity is going to be the breadth divided by 2, and here is going to be the length divided by 2. Here is actually it's actually the height, okay, over 3, okay, the height over 3, the height over 3. That's the center of gravity, the center of gravity. So it depends. For vertical surface, D depends on the center of gravity of that of the ship, of the bulkhead, or of the gate. Depends on what we have, okay. And if it's a circle, so let's say we have a circle, our reference point is a circle, okay, let's say like a manhole, manhole or anthole. So the center of gravity is going to be at the center, which is actually the radius, okay, but also don't forget from the surface, okay, so which is going to be the radius, or we can say diameter over 2, okay. That's number 2, second thing I want to point out. Now the third thing I would like to point out in solving questions is, okay, so the third thing I want to point out is we said thrust is pressure times the area. Again, area is the area of the the surface in question. Okay, covered or occupied by the fluid, which is water. Okay, so if the shape covered by the fluid, by the water, is rectangle, let's say something like that, a vertical bulkhead, and is filled with water, yes, then we know that okay, it's covered by, it's taking the shape of that rectangle, then that means our D is going to be from here downward, okay, which is the height over 2, okay, and our area is going to be length, let's say length and breadth, so length times breadth. But if say it's like that, okay, at a particular height, then we say that G is going to start from here upward up to where the water surface is, and then our area, let's say this is draft, and our area is going to be the shape occupied by this rectangular water, in that sense, okay, length times strength. So we need to we have this kind of shape instead. Let's use this. So if, let's say, water, we have water here, so we know this is the surface, and when you go down, okay, this is the surface, this is the shape we are considering, okay, so that's a rectangular shape. So D is going to be from the surface to the centroid of this guy, and we know that centroid is the height, okay, the height of this shape, okay, so D is going to be h over 3, okay, which is from here to here, so it's going to be from here to here, h over 3, okay, and the area is going to be the area occupied by, okay, by the water shape, which is half base times height. So this is the base and this is the height, okay, so it's just as simple as that. The first question we'll be solving, number 1, says find the thrust experienced by a flat keel plate 20 by 4 meters when the draft is 6. So we have the area of the keel is 20 meters by 4 meters, okay, which is, we have the length and this is the breadth. The draft D from the water surface is 6 meters, and the seawater is actually, the density seawater is 1.025 tons per meters cube. So they said flat surface. So if this is the shape, for example, let's say this is the shape, okay, this is the shape. Now this is the keel, we have water, so this is 6 meters draft. So from the water surface to the keel is 6 meters. So they said find the thrust. So we know that thrust is the pressure times the area from the previous proof. We also know, so that means we have to find the pressure and then we multiply by the area. Now we know that pressure is density times the depth. So density of water is 1.025 times, and the depth, which is the draft from the water surface, is 6 meters, okay, and then we can have it like 1.025 times 6. So we have 5 times 6, we have I'm going to do it again, 1.025 times 6, we have 6.15 tons per meter squared. So we know that thrust is P times A, and then it's 6.15 times, so the area is 20 times 4, okay. So here we understand that we just use the depth as it is, and we use the area as the area of the rectangle, because the keel is a rectangle. According to this, it's a rectangle. So the keel, if we look from the top like that, okay, that means it's going to look like that. Okay, so the pressure is acting that way on the keel. So length times breadth. So we say 6.15 times 20 times 4 gives us 492 tons. And that's it. Now, number 2 question says a box shaped vessel. So this is the vessel. It's a box shaped vessel. The length is 120 meters. So this is actually length times breadth times height. So the breadth is 20 meters and the height is 10 meters. So it's floating in a dock of relative density 1.01. So we know that the box has a length of 120 meters, a breadth of 20 meters, and a height of 10 meters. The density of water surrounding it in the dock is 1.01 tons per meters cube. Now, the water is actually is 8 meters in draft, so means it's touching it on the side. It's surrounding, okay, surrounding the surrounding. This is the water. Okay, it's surrounding it because it's immersed. The box, which is the ship, the vessel, is immersed in water. So that automatically tells us that the draft is 8 meters, like that. Okay, and remember the word even keel. So it means that the forward. So if we say this is the forward, this is the forward, this is the aft, this becomes the starboard, and the other end here we have the port. Okay, so on all sides it's 8 meters draft. So it's 8 meters draft on all sides. So let's say find the total water pressure exacted by the hull. Now, one thing to understand is that the water is actually exacting pressure on the forward, on the aft, on the starboard, on the port, and also on the keel. Okay, it simply means where on the body of the ship where water is touching. So it's touching the keel, it's touching the starboard, forward, port, and then aft. So in this case, we can say that thrust is acting in this direction. It's acting on this side, it's acting on this side, it's acting on this side, it's acting on the port side, and then it's acting on the keel. So the total thrust will now be the thrust for the aft, plus the thrust for the forward, plus the thrust for the starboard, plus the thrust of the port, and the thrust for the keel. Okay, so what is the thrust? Let's take one after the other: the aft, and the keel, and the forward. Okay, so we can say here that thrust will be P times A. P is rho D and then times A. Then rho is 1.01 times, what's the depth, okay, of water surface to the centroid? Because this time around, if we look at it, this is the forward, and here we have the aft. So they are of the same depth, same depth, same water, everything is the same. Okay, so the depth, like we said here, it's a vertical consideration. Okay, vertical surface. So if we look at this water for the aft, it's actually a vertical plane surface. So it means that the depth is going to be from the water surface to the centroid. So, and we know the draft to be 8, right? So it's going to be 8 over 2, because this is a rectangle, right? So if this is a rectangle, and we are considering the height from the water surface, right, the depth, so it's going to stop here at the centroid of this rectangle. And what's the area covered by the box? Okay, so it's the draft, okay, times the breadth, which is 8 times 20. Now it's going to be the same for the forward and the aft, so we can multiply it by 2. So that gives us, this cancels this, so that gives us 1.01 times 8 times 8 times 20. Okay, so we have 1292.8 tons. Okay, so we're going to do the same for starboard and the port side. Again, the thrust is P times A, which is rho dA. Rho is still the same water of the dock, where it is immersed, right? The draft, again, is also going to be from the water surface, okay, from this water surface. So if we look at this, you see that this is what, this is the plane surface area of the starboard. The same thing for the port as well, on the other side, on the other end. So the depth, again, is going to be from the surface of the fluid, of the water, to its centroid. And what's the centroid? So the height is the same draft, 8 divided by 2. Okay, centroid of a rectangle is the height divided by 2. Then the area, like I said, is this shaded portion, which is, if you look at it, it's a rectangle. So the area is always the area covered by the water, occupied by the water. So which is the draft, 8 times 120. So 8 times 120. Again, this is for starboard. To get for both sides, port and starboard, is going to be times 2. This cancels this. Then we have 1.01 times 8 times 8 times 120. So we have 7756.8 tons per tons. Okay. Then we can also do for the keel, and then we add them together. So for the keel, it's just one keel surface that we have, which is, then we say T is equal to P times A, rho dA, 1.01 times the depth. Okay, now we are talking about the horizontal surface now, which means that we take it as it is, the draft as it is, and the area as it is, you know. So the draft is a main draft. We're not divided by 2 now, because it's from the water surface down to the keel. It's not a vertical plane, it's an horizontal plane. So we say the draft is 8, it's going to be 8, okay, not divided by 2. We don't have divided by 2 here. So the area is the plan, okay, which is the keel, the plan, which is, I'm going to shade it out with, let's say, this color. So it's going to be like that, and that. So this base area is what we need, which is 120 by 20. So we have 120 by 20. Okay, so we have it. So we don't multiply by 2 this time, because it's just one keel we have. So 1.01 times 8 times 120 times 20. So we have 19,392 tons. So the total thrust will now be from this formula. So we add this to this and to this. So it's going to be 1292.8 plus 7756.8 plus 19392, which would be give us 1292.8 plus 7756.8. So we have 28,441.6 tons. Okay, so that's that. Now the next question is, okay, I'm going to put it on the side. A submarine has a surface area. Okay, so the surface area of the submarine is 600 meters squared. Oh, okay, this one is not supposed to be here. And can withstand a total pressure of 1333000 tons. Find at what depth, okay, in seawater would it collapse. So the seawater tells us that the density is 1.25 tons per meters cube. So we can say that, you recall that thrust, water pressure. Okay. Okay, thrust is P times A, and T is equal to rho D times A. Okay. Now, because this, it's good to understand that this unit is in tons from here. So meaning that this number here, this parameter is not pressure, it's actually thrust. Because the unit of thrust is tons. So we're going to substitute that value here. So we have 1333000, density is 1.025. We're looking for the draft, and we know the area to be 600. So the draft will now be 1333000 by 1.025 divided by 600. So that's going to be 1333000 divided by 1.025 divided by 600. So it's going to be 2167.4 meters. Okay. A rectangular lock, number 4, the fourth question now. A rectangular lock gate. So rectangular lock gate. Okay. Rectangular lock gate. So rectangular lock gate. 50 meters wide and 26 meters high. So we need to understand this wide, okay, and the height is 26 meters. So this is 26 meters height, and there is 50 meters wide. The water inside the lock is 9 meters deep. So inside this lock, I'm just going to try and do this to differentiate between the inside so we don't mix things up. So the inside is this, okay. The water inside is 9 meters deep, 9 meters. And the density of that water is 1.005. Okay, 9 meters deep, density is 1.005. The relative density, I mean. Now the water outside is 6 meters deep. Okay, so outside this gate, the water is 6 meters deep. It's 6 meters deep. From the water surface. Now the density of that, the one outside, is 1.025. So find the resultant thrust. Okay, resultant summation. Resultant means the summation of all the forces, of all the thrust, and direction with which it's at. Okay, let's understand again. The water inside is 1.005 and the draft is 9. The one outside is 6 meters draft, and the density is 1.025. Now for the inside, we say thrust is PA, that's rho dA, and so rho for the inside is 1.005 times the depth. Okay, so the depth, again, you have to understand that we are considering a vertical plane surface here. So the yellow water, which now goes to the center, so it means that's half of the vertical, which is the centroid. Okay, so 9 divided by 2 times the area of the space occupied by the water, which is this one right here. Okay, so that's going to be 50. The length of this water is 50, and the draft is 9, right? So it's going to be 50 times 9. So we have 1.005 times 9 times 50 times 9 divided by 2. So we have 2035.125. So we're going to do the same for the outside now. Outside, T again is PA, rho dA, and then this density for the outside is 1.025 times the depth again to the centroid, right? So it's going to be, because it's still it's also a vertical plane reference. So it's going to be 6 divided by 2, and the area is this one right here. I'm going to use this one. It's this one right here. Okay, so it's this one right here, occupied by. So therefore, what's the area occupied by that water on the gate? On the gate, actually. So it's going to be 6, okay, times 50. So which is 50 times 6, and that should give us 1.025 times 6 times 50 times 6 divided by 2. So we have 922.5 tons. The unit is tons. So the resultant thrust will now be whichever is bigger minus the smaller value, so which is 2035.125 minus 922.5 T. So we have minus 2035.125. So we have 1112.625 tons. Now, in what direction is it? The inside is acting on the gate, right? Outward. The outside is acting on the gate inward. So it's going to be outward because the inside water is more than the one outside. Okay. A rectangular lock gate. 40 meters wide and the height is 22 meters. So it's 40 meters wide. It's fresh water on one side to a depth. So one side of this gate we have fresh water, okay, to a depth of 14 meters. Okay, fresh water means the density is 1 tons per meters cube. Find what depth of seawater on the other side. So on one side, okay, on this side we have fresh water. Now on the other side of this gate we want to apply seawater on the other side just to balance it. So what's the depth that will equalize the thrust? So equalize means that the condition is that the thrust on the seawater side needs to balance the one on the freshwater side. Okay, so the thrust for seawater formula is pressure times area, and this is also pressure times area, and then we say rho dA is equal to rho dA. Now the densities are different because it's for the seawater, so we can't cancel out. The depth is what we're looking for. Okay, the depth we know, this is freshwater. The depth we know, this we don't know. The area we don't know, obviously, because we don't. Area is the shape occupied by the water. So the density of seawater is 1.025. The depth is what we don't know, but that depth is going to be d over 2 because it's a vertical surface. We don't know, right? It's going to be from the water surface to the centroid, then times the area. Okay, for the seawater, right? Even the area we don't know. Okay, but we don't know because we don't know the depth. But normally it's supposed to be length times breadth, right? So we know the length. So let's say it's right here. Let's say the other side seawater is right here on the other side. Okay, we are looking for the depth, right? So what is going to be the shape occupied by that surface? If you can see, it's 40 by the draft, which is the depth. So we're going to say this is d, which is length times breadth anyway. So just going to say length times breadth. Length is 40 times the depth. Okay, be equal to 1 times, we know the draft for this guy, for this freshwater, the draft is 14, which is the depth, but 14 divided by 2 because it's a vertical surface. The area is the area occupied. Okay, we've talked about this. Is the area occupied by this guy here, so which is 14. Okay, we know from here to here is 14, so which is 40 times the length times breadth. 40 times 14. 2 can cancel 2 and 40 can cancel 40. Okay, so we have 1.025 d times d is d squared. This is what we have left, 14 times 14. So d squared can then be 14 times 14 divided by 1.025. What do we get? So we have 191.21951. So d is now the square root of 191.21951. So square root of that, so the square root of my answer is 13.828 meters. So in order to balance, back to the question now, in order to equalize the thrust, when seawater is acting on one side, freshwater on the other side, the freshwater on one side is 14 m depth okay, 14 m deep. So in order to balance this, the sea water, okay, on the other side has to be 13.828 meters deep. A collision bulkhead is triangular in shape. Its maximum breadth is 12 meters. The height, so I'm just going to draw this again. So the breadth, which is this end, is 12 meters. Its height is 15 meters. Find the thrust experienced by the it if the forepeak tank is pressed up. So the forepeak tank is now pressed up. Three meters above it. It's pressed up. So 3 meters of seawater. So from here to here is 3 meters. Okay, so again, it's pressed up means that it's filled up and then up to that. So find the thrust experienced. So again, we know that thrust is pressure times the area occupied by that water. So by that water for the ship. So pressure is equal, so rho dA. So what's the density for seawater? We're dealing with seawater, so 1.025. And then the depth of water from the surface, okay, from this surface, which is 3 meters, to the centroid. The centroid is right here. The centroid is right here, which is, like we said, from the base to the centroid is always h/3, meaning that from the entire surface down to the centroid is going to be 3 plus h/3. So 3 from here to here is 3, and from here to here is h/3. So we have 3 plus h. Okay, h is 15 divided by 3, which is 3 plus 5, and that's 8 meters. So it means the depth is 8. The depth is 8, and the area is the area occupied by this water on this ship of concentration. So which is half base times height, because it's a triangle. So 1.025 times 8 times half base is 12. Okay, base is 12 times height is 15. Then we have 0.025 times 8 times 12 times 15 divided by 2. So we have 738 tons, and that's it.